In this online lecture, we're going to talk about how to do conformational analysis on cyclohexane, and I recommend that you watch the introduction lecture first. And what we're going to learn in this lecture, though, is one, that axial substituents are gauche with a carbon in the ring, and equatorial substituents happen to be anti with a carbon in the ring. We're also going to see, number two, that axial substituents have two what's called 1,3 diaxial interactions. And we're also going to see three, that axial substituents are higher energy than equatorial substituents. Let's understand each one of these key points, and let's talk about how we use them to do conformational analysis. So let's start here. This, remember, is our chair cyclohexane. And let's put an axial methyl on this carbon right here. What I want you to know is that that methyl happens to be gauche with one of the carbons within the ring. Now, you can't really see that here. You're going to have to take my word for it. I'm going to give you proof of this in a few minutes. Now, here's something else I'd like you to know. Let's just randomly place a methyl group. Let's put him right here and let's make him equatorial. I want you to know that all equatorial substituents are always anti to a carbon within the ring. Again, I'll prove this in a few minutes. And the other thing I want you to know is that always the axial position is the higher energy position or less stable position, and the equatorial position is always going to be the lower energy, more stable orientation. We need to walk into our next orgo exam with these at our fingertips, and that is, again, axial substituents are gauche with a carbon in the ring, and that is equatorial substituents are anti with a carbon in the ring. This information right here in front of you is going to help us do conformational analysis. But let's not just memorize this, let's understand this. For instance, let's say this is chair cyclohexane right here. And let's try to think in 3 dimensions. Let's say that, remember, it folds about these lines right here. And imagine that you're looking at the molecule from this perspective. Think about this. If you were to, let's say, move to the right like this, you would see this carbon in the front and you would see this carbon in the back. In other words, that carbon would be the front right carbon from your point of view, and the other one would be the right back carbon. What I want to do here is generate a Newman projection of chair cyclohexane, and you're going to see that that's possible. Remember, Newman projections represent always a carbon in the front and the carbon in the back. So this is what the Newman projection would look like for that right-hand carbon. The small blue dot would be the carbon in the front. The big round blue circle would be the carbon in the back. Now, go back to our chair structure here. If you were to look, let's say, to the left here, again, you would see a carbon in the front and you would see a carbon in the back. And these two carbons would be level with the front right and right back carbons, which means this is what they would look like in a Newman projection. What you see here on the right is the Newman projection of chair cyclohexane. And let's take a second to make the connections here so that you can see this. Look at our chair cyclohexane. Notice it's the two front carbons that are both directly connected and point downward to this carbon right here with the green dot. Look at our Newman projection. That would be this carbon right here. Now notice the back carbons. They're both directly connected to the same carbon, which would be this carbon right here in the green dot. In our Newman, that would be this carbon right here. Take the time to make these connections. Notice you will, in the Newman projection, count 6 carbons in that ring. Now, watch what happens here. I'm just going to place a methyl axial, and I'm just going to place it here on the front left carbon. Let's now place this exact same methyl in our Newman projection. He would be right here, again, on the front left carbon. Notice the angle that's between this methyl right here and the green back carbon in our Newman projection. They happen to be 60 degrees apart from each other. And remember, when you have two carbons that are 60 degrees apart, that's the dihedral angle, then these two carbons would be considered gauche to each other. This is what I mean by axial methyls always being gauche to a carbon within chair cyclohexane. I need you to know that this is true for all axial positions. I'm only putting my methyl here specifically because you can see it best at this location. Now, here's the other thing I want to prove to you. Let's put a methyl on the front right carbon and let's make him equatorial. This is what he would look like. And now let's place him exactly where his location is on the Newman projection. He would be right here, the equatorial right front carbon. Notice the angle between this methyl and the same green carbon within the ring. If you notice, they are actually 180 degrees apart, meaning this methyl is 180 degrees to this carbon in the ring. And remember, in this case, that's called anti. Or we say that methyl is anti to the carbon within the ring. So this is proof of our two important key points. One, again, remember, axial substituents are gauche with a carbon in the ring, and also equatorial substituents are anti with a carbon in the ring. We'll never have to go back to these structures. We can just simply remember these points. And while we're looking at this, remember, what did we say before in a previous online lecture about the energy difference between a gauche interaction and an anti-interaction? If you remember, we said gauche interactions are higher energy than anti-interactions. Keep that in mind. We're going to come back to that principle in a few minutes. However, there's something else I want to show you here. Let's again say we have chair cyclohexane, and let's place a methyl in this axial position right here. And let's say this is the only substituent on the ring. The rest are hydrogens. But let's look at these particular hydrogens right here in the axial positions. And let's also do this. Let's expand our methyl out. Remember, he really looks like this. The three hydrogens project outward away from him. Think about the steric consequences here. For instance, remember, these would be the s orbitals of the hydrogens that would overlap to make the bonds to the carbons. Look at the proximity of that methyl hydrogen to those two hydrogens within the ring. He's pretty close to this guy right here, and he's close to this guy over here. This means that we have a steric situation right here. We have orbitals close to each other, which means electrons are going to be close to each other, which is going to be higher energy, less stable. We need to know that this is the situation for an axial substituent. And there's a name for it here. For instance, let's say that this methyl happens to be on carbon 1. Notice where these hydrogens are on the ring with respect to that carbon. This would be the possible carbon 2s right here, and this would be the carbon 3s right here. In other words, the axial methyl on carbon 1 is 3 carbons away on the ring from each of those axial hydrogens. That's why the name of this interaction is called a 1,3 diaxial interaction. We're simply learning again that all substituents that are non-hydrogen always have a 1,3 diaxial interaction with either hydrogens or substituents that are 3 carbons away on the ring. But notice here, it's not just one 1,3 diaxial interaction. This is one right here, and this is a second one right here. In fact, here's our principle that we need to remember, and that is axial substituents always have 2 1,3 diaxial interactions. So what does this all mean? We're now ready for a very important principle here. What we're saying is that if there's a substituent that's not a hydrogen and he happens to be axial, we saw first that this substituent would be gauche with a carbon within the ring. We also saw that he would have something called 1,3 diaxial interactions, and he'd have 2 of them. Both of these, remember, would be considered higher energy or relatively less stable. So pulling these two things together, here's our key point. I need you to know that axial substituents are always going to be higher energy than a substituent located in an equatorial position. This is the fact that helps us do conformational analysis of cyclohexane. And let me prove that to you. Let's look at a sample problem here. This one says, draw the most stable conformation of trans 1,4 dimethyl cyclohexane. Now let's piece together all the principles that we've learned so far about this type of conformational analysis. We'll start with one that we learned in a previous online lecture, and that is, remember, chair cyclohexane is the lowest energy conformation. So that's the structure that we would want to start with, meaning we wouldn't draw up boat or half chair cyclohexane. So that takes care of step one. And of course, we draw out our template of cyclohexane. Then we remember this principle that we learned in this lecture. Axial substituents are always higher energy than equatorial substituents. Which means let's start to construct the molecule. Remember, we have to place two methyls and they need to be trans. Let's place the first methyl right here, but let's put him equatorial because remember, we know that that is the preferred lower energy orientation. Now we got to stick the other methyl on this molecule. Well, it's 1,4 substituted, so we should walk over to carbon 4 here. But remember, we have to satisfy the whole trans relationship. So if that first methyl is equatorial and pointing downward, we would want our next methyl on carbon 4 to be pointing upward. And upward in this case, remember, would be equatorial because axial is downward. So we place our methyl right here, and now we know he's equatorial. Which means this is our answer. This would be the most stable conformation of trans 1,4-dimethyl cyclohexane. This is a typical question or skill in organic chemistry. We rarely are asked the question about the highest energy conformation of a cyclohexane because the answer to that is very simple. The highest energy conformation, remember, is half chair. You would simply draw a half chair cyclohexane, place the methyls on it, and that's your highest energy structure. Which means there's really no analysis in that question, whereas this question, most stable conformation, requires much more analysis and more principles to lean on. Now, to help you master this skill, let me do the same problem but a little differently here. It's going to combine other skills that we learned before. Let's say, for instance, when we started this problem, we drew our chair cyclohexane and happened to put the methyl here in an axial position instead of equatorial. Then, if we wanted to place the second methyl here, we would walk over to carbon 4. And remember, they need to be trans to each other, these methyls. We have the equatorial and the axial like this. So the other methyl would be facing here in the downward direction. So he's trans to the methyl on carbon 1. Now remember, we know that axial substituents are higher energy than equatorial substituents. So if we drew this structure, this would be higher energy than the previous one we drew. But remember, we know this principle, that chairs have the ability to ring flip. And the principle is, ring flipping this chair would cause all the axials to become equatorial and all the equatorials to become axial. Which means here on carbon 1 and 4, the methyls would convert to their equatorial positions. Which tells us that the conformation on the right here would be the correct answer to the original question. This is again why it doesn't matter if you put the substituents axial or equatorial, because in your conformational analysis, you're most likely going to ring flip it anyways to make sure that you got the most stable conformation. However, time is of the essence on an orgo exam. That's why I recommend always putting the first substituent equatorial. So again, notice the relationship here from what we did before. What we got as an answer in our analysis was that the most stable conformation of trans 1,4-dimethyl cyclohexane happened to be that the methyls are 1,4 apart and that they're both equatorial. And again, with a substitution of 1,4. So let's look at another problem here. This one says, draw the most stable conformation of cis-1-ethyl 2-methyl cyclohexane. Again, we'll start out with our general template right here. And to save time here, let's work smart. Notice we have two substitutions, an ethyl and a methyl. To get to the answer quicker, let's pick the more bulky substituent, which in this case would be the ethyl, because he's 2 carbons compared to methyl, which is only 1 carbon. And let's place him in the equatorial position. Now, let's walk over to carbon 2 now. Here's 1, here's 2. And let's place our methyl, and let's make sure that he's going to be cis to the ethyl. And again, remember, we know our general template. This would be the equatorial bond. This would be the axial bond. And the ethyl happens to be in the down position. So to be cis, the methyl should also be in the down position. And in this case, that would be the axial position. So here is at least cis 1 ethyl 2 methyl cyclohexane. Now, to be sure, is this the most stable conformation? Well, we know, remember, this thing could ring flip. And when it does ring flip, remember, all axials become equatorial and vice versa. So the ethyl will become, on carbon 1, let's say, axial. And the methyl on carbon 2 would become equatorial. So notice, in both ring flip structures, we have at least one substituent that's in the higher energy axial position. The question is, which one would yield the lower energy or more stable structure? Well, think about it. In the ring structure on the left, the more bulky substituent is equatorial, and the less bulky substituent is in the axial position. That's the exact opposite over here. The more bulky is in the higher energy axial, and the less bulky substituent is in the lower energy equatorial. So we'd rather have our more bulky group to be in the lower energy equatorial position, so that means this structure on the left is the most stable and therefore is the answer to this question. Now keep in mind some test-taking skills here. I wouldn't want you to actually draw out the ring flip version of this molecule, meaning you would just draw the first one and you would just in your head think about if the molecule were ring flipped, equatorial would convert to axial and vice versa. And just thinking about that is enough to know that this structure here on the left would end up being your lower energy, more stable structure. I'm only showing you the ring flip version for proof. Now, let me show you another sample problem here. I want to show you that this is possible. This can happen. Let's say they're asking us to draw the most stable conformation of cis 1,4 dimethyl cyclohexane. Again, we generate our template right here. Let's put the first methyl equatorial, why not? And let's count over to carbon 4 here to place our next methyl. And we remember our bonds here. We got the equatorial pointing up and we got the axial pointing down. We want a cis arrangement here. So if the methyl on carbon 1 is pointing downward, then we want the methyl on carbon 4 to also point downward in the axial position. So here is our molecule. And let's stand back and think energetically here. We got one substituent equatorial, low energy. We got another substituent in the axial, higher energy position. And in our head, we should think that if we ring flip this structure, this is what we should get. Again, 1,4 substituted, equatorial methyl becoming axial, and the axial methyl becoming equatorial. Now, if you were to think about the relative energies of these structures, they both have an axial methyl and an equatorial methyl. So in this case, the ring flip versions are of equal energy. They are equally stable. So sometimes neither ring structure is more stable than the other. But again, connecting this to a multiple choice test in organic chemistry, you're looking for an answer that has the two methyls 1,4 apart. They are cis to each other, in this case both pointing down or both pointing up, and one is axial and the other one is equatorial. That's enough information to pick out an answer choice in a lineup. Now, let me show you another problem here. Sometimes on a test, they'll represent a molecule this way, and they'll ask you which one is the most stable conformation of this molecule. Well, notice it's a 6-membered ring, so it's definitely some kind of chair structure. And let's do this. Let's number our carbons, not by nomenclature. Let's just number them to reference. For instance, let's say that's carbon 1. This is 2, 3, 4, and 5. This is just to help us know how far apart the substituents are within the ring. So for instance, I'll start right here and say this is my carbon 1 that happens to have the Cl on it. And to quickly get to answer, let's place him in the equatorial position. Then we'll walk over to carbon 3 and watch this. For this particular example, I'm going to go a different direction. And I'm going clockwise here. In all the other examples, I went counterclockwise around the ring. This is just to prove to you that it doesn't matter which way you go around the ring. You're going to still end up with the same answer, and that's the beauty of this type of conformational analysis. But I recommend that if you typically go clockwise or counterclockwise, that you stay in that direction when you do these types of problems. Now the question is, how should I place that methyl on carbon 3? Well, look what the two-dimensional structure given to us is telling us. Notice, remember, this bond wedged solid means coming out of the board, and this bond right here means it's going into the board. The question is, how do we translate that to chair cyclohexane? Well, it's probably what you would think. Out could be, for instance, up, and in could be down. Or out could be down and in could be up. All that matters is that these substituents are trans to each other, basically. So that means, look at our chair cyclohexane. If I put the Cl in the down position, then trans to him would be the up position. So I should make the methyl in the axial orientation. Now let's place this last substituent here. Here's carbon 4. Here's carbon 5 right here. Again, look at the two-dimensional structure and notice the relationship. The methyl on carbon 5 has a solid wedge, so we can say he's facing outward. And there's technically two ways to do this. You can say that the methyl on carbon 5 is cis to the Cl on carbon 1, or you can say the methyl on carbon 5 is trans to the methyl on carbon 3. So for instance, let's compare it to the Cl. Remember, in our chair cyclohexane on carbon 1, Cl is pointing downward. And if the methyl on carbon 5 is cis to him, he should also be pointing downward. And downward at this particular location happens to be equatorial. Notice, compare also the methyl on carbon 5 in the chair cyclohexane to the methyl on carbon 3. The methyl on carbon 3 you can see is pointing upwards, and the methyl on carbon 5 is pointing downwards. And that's exactly what's revealed in the structure on the left. Again, that's the beauty of this system. So now that we've generated our structure, let's do the energy analysis. Notice we have a Cl that's equatorial, we have this substituent right here that happens to be axial, and this one ended up being equatorial. That gives us 2 equatorial substituents to 1 axial substituent. Right there you should decide this should be our lowest energy structure. Because again, if you think about the ring flip version, we would know that both equatorials would become axial, and the one axial would become equatorial, as you see here in the structure below. So that means this is our most stable conformation, and therefore this is the answer. So what have we learned here? Well, our first key point we saw is that axial substituents are gauche with a carbon in the ring, and equatorial substituents are anti with a carbon in the ring. We also saw number 2 that axial substituents always have 2 what's called 1,3 diaxial interactions. Which led us to point number 3 is that axial substituents are the higher energy orientation than equatorial substituents. And it's this last key point that really aids us in our conformational analysis of cyclohexane.